All right, we're on to the last 2 pages. Great. So, starting up, number 48. A disk has a moment of inertia of 3 times 10 to the negative 4th kilogram meters per second squared and rotates at an angular speed of 35 rads per second. What net torque must be applied to bring it to system to rest in 3 seconds? All right, so they want us to take Newton's second law, F equals ma, and use the rotational version. Torque is equal to I times angular acceleration. All right, and so the question is, what angular acceleration do I need in order to stop it in 3 seconds? So let's figure this out. If the initial angular velocity was 3.5 rads per second, and the final angular velocity is equal to 0 rads per second, then the angular acceleration is what we're trying to find, and the time being 3 seconds. So we can just use the basic equation. Angular acceleration is equal to final minus initial angular velocity divided by the time. All right, so we have 3.5 rad per second minus, no, the final is 0. 0 minus 3.5 divided by the time of 3 seconds gives us something very, very close to 1. 3.5 divided by 3, an acceleration of negative 1.167 rads per second squared. So that's the acceleration we got, and so we can plug that in over here. So torque is what we're trying to find. The I they gave us was 3 times 10 to the negative 4th, and then the acceleration we found was negative 1.167 rads per second squared. And so that gives me my torque if I just multiply those two numbers together. So 3 times 10 to the negative 4 multiplied by negative 1.167. And I get this number, which I can put into scientific notation by hitting second degree, switching it to scientific mode. 3.5 times 10 to the negative 4, which is option C. They dropped the negative, though. I didn't. Okay, next one. A ventilation fan with a moment of inertia of 0.034 kilogram meters squared has a net torque of 0.11 Newton meters applied to it. If it starts from rest, what kinetic energy will it have 8 seconds later? So, again, we're going to apply this rotational torque equation, rotational Newton's second law, and we can figure out what the acceleration is. So we're going to take the torque they gave us, which was 0.11 Newton meters, not the same thing as like joules, just similar units, divide it by the I, which was 0.034 kilogram meters cubed. All right. Oh, no, squared. Not sure why I wrote cubed. I said it like quite certainly as well, but that's just my tired brain. All right, so 0.11 divided by 0.34 gives me an angular acceleration of 3.24 rads per second squared. Okay, so that's great. We have our acceleration. So now we want to figure out how fast it'll be going angularly after 8 seconds, okay? So how fast will it be going? Well, that's equal to initial plus angular acceleration times time. So they gave us 8 seconds, and it starts from rest, so the initial is going to be 0, so we just have to take the acceleration we just found, rad per second squared, multiplied by time, 8 seconds, like that. All right, so therefore 3.24 times 8 will give me a final angular speed to 25.92 rads per second, which is pretty quick. Now the question's asking for the kinetic energy, and there is an equation for kinetic energy of something rotating. It's the same as the regular kinetic energy equation, 1/2 mv squared, just with rotational variables. So m is I, and velocity is omega squared, or w, whichever one you prefer. I really don't care. So 1/2 I omega squared. So 1/2, the I they gave us was 0.034. And then the angular velocity we just found was 25.92, and that'll be squared. And we plug in those numbers into a calculator and solve. So 1.5 times 0.034 times 25.92 times 25.92. That gives me 11.42 joules. The closest answer to that is 11. So that's answer C. Don't be afraid if you get 11.4 and the answer is 11. They do that a lot. They often approximate and round numbers to the nearest thing. It's going to make you second guess yourself, but don't worry about it. The total kinetic energy of a baseball thrown with a spinning motion is a function of, well, if you want to figure out the total kinetic energy, you have to consider how fast the ball is going and how fast it is rotating, okay? So it's going to be a combination of the kinetic energy regular plus the kinetic energy rotational. All right, so it's linear speed, but not its rotational speed. It's rotational speed, but not its linear speed. Both linear and rotational speeds. Yeah, you got to consider them both. Okay, what that means is if this is 1/2 mv squared plus 1/2 I omega squared equals the total kinetic energy, the kinetic energy is a function of these two letters, these two variables. A tether ball is attached to a pole with a 2-meter long rope. It's circling at 0.2 revolutions per second. As the rope wraps around the pole, it shortens. How long is the rope when the ball is moving at this speed? So what the heck is this question asking us? Well, it's asking us to consider conservation of angular momentum. Now, very similar to regular momentum, where conservation looks like this, m1v1 plus m2v2 equals m1v1 final plus m2v2 final. Very similarly, we can apply the same thing here, where instead of m, we use I, and instead of v, we use omega. Now, except we don't really write out all of the different things. Okay, we don't write out things because we're only dealing with one object in angular momentum's sake. Okay, so this is a really interesting one because what's happening is the tether ball on the pole is stretched out really far, and as the pole gets wrapped around, the ball is going to kind of wrap around the thing and end up much closer to the pole. And when it does that, since angular momentum must be conserved, it must gain a larger omega than the one that was up here, much smaller omega. So let's replace I with the equation for I, which is mr squared. Omega I is equal to mr squared omega f. Now there's going to be an initial radius and there's going to be a final radius. Now, how long is the rope when the ball is moving at this speed? Well, the rope's length is going to be equal to the radius, so let's figure that out. So the ball's mass can cancel out, but the radius are going to be different. Okay, so it says there's a 2-meter long rope initially, so we'll make that 2 squared multiplied by the initial velocity of, they didn't give us the initial velocity, they gave us the frequency. So the frequency is the number of rotations per second, and it does 0.2 hertz, or 0.2 rotations per second. To get the angular speed, we'll have to use 2 pi times the frequency, which is an equation on your reference table. So 2 pi times 0.2 hertz is going to give us our angular speed. 2 times pi times 0.2 gives me an angular speed of 1.257 rads per second. So I can plug that into my equation, 1.257 rads per second. That should be equal to the new radius, which is what we're solving for, our final squared. That's what we're looking for. And the final angular velocity, ooh, they didn't give us the angular velocity. They gave us the regular linear velocity. So in order to figure out what the actual angular velocity is, we're going to have to use this equation. It's equal to omega times r is equal to v. And so omega is equal to v over r, which they gave us 5 meters per second. And this r is going to be r2, the radius at that point. So this times 5 meters per second over rf, like that, which is actually really useful because rf will cancel here, and so we'll be left with 1 rf. And so all we'd have to do is solve for this and divide by 5. So let's write it out in a place with a little bit more space. The equation I had here was I omega I equals I omega f. Now I replaced this initial squared, omega I is equal to m r f squared omega f, and so the m's canceled. Now this initial radius was given to us, it was 2, and so we'll square that. The angular velocity we had to calculate, 2 pi frequency, which became 1.257. Now, and then we were solving for RF, and we did not get the angular velocity. We had to solve for it using v over r. The v they gave us was 5 meters per second. Divide that by RF, and the RF's canceled. So this is where we're at. And so I'm going to solve that whole side. So 2 squared times 1.257 gives us 5.03 meters. I'm not sure if that's meters. Angular momentum is going to have complicated units. It's kilogram meters squared over seconds, I think, or kilograms squared. I'd have to look at the equation, but you could figure it out. So that should be equal to RF times 5. So you just divide it by 5, and so you're going to realize it's practically 1. 1 meter is equal to the radius, which is an option D. Lastly, a pendulum on Earth has a period of t. Okay, and as soon as you read that, you should think, okay, is there an equation for a pendulum? And there is. 2 pi square root of length of the pendulum divided by g, like that. So the acceleration due to gravity on Mars is less than on Earth, and the acceleration of gravity on the moon is even less than Mars. Where would the period of an identical pendulum be the least? Okay, so you got to think, if g is controlling this, Earth has the largest g, so the period would be the smallest. Then the moon would have the smallest g. Since you're dividing by a smaller number, the moon's period would be the longest. So where would the period of an identical pendulum be the least? That would be on Earth.